The stopwatch clicked in Dieter Hoffmann's hand as the bare steel frame touched down on Station 1 of the assembly line. It was the morning of May 17th, 1945, and the war in Europe had been over for 9 days. Hoffmann, a senior automotive engineer who had spent 12 years perfecting production methods at Volkswagen's Wolfsburg plant, stood in the cordoned observation area of the Willys Overland factory in Toledo, Ohio. His American escort had handed him the stopwatch with a simple instruction: time, how long it takes to build a Jeep from major components to a vehicle that can drive under its own power. Hoffmann had smiled politely, assuming this was some sort of propaganda exercise. In his experience, assembling a military vehicle properly required 4 to 5 hours of careful work by skilled craftsmen. He reset the stopwatch to 0, his thumb hovering over the start button. What he was about to witness would shatter every assumption he held about industrial production, national power, and the war his country had just lost. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Hoffmann had been captured 6 weeks earlier, outside Kassel, as American armored units swept through Germany's industrial heartland. He and several dozen other engineers from German automotive plants had been identified as high-value technical personnel and separated from regular prisoners. The Americans told them they would be consulting on technical matters related to industrial production. Within days, they were on a transport ship to America. The journey across the Atlantic took 12 days, and Hoffmann spent much of it trying to understand why the Americans wanted German engineers to see their factories. The war was over. Germany was defeated. What purpose could this possibly serve? Now, standing on the factory floor in Toledo, watching that bare frame begin its journey down the assembly line, he was about to learn the answer. The Americans didn't want him to consult. They wanted him to witness. They wanted him to understand, with absolute clarity, why Germany had lost not on battlefields but in factories, not through inferior tactics but through impossible mathematics. They wanted him to see American industrial capacity with his own eyes, so that he could testify to it for the rest of his life, so that no one could dismiss his account as Allied propaganda or defeatist thinking. He pressed the button. The stopwatch began counting. And in less than 15 minutes, everything Dieter Hoffmann believed about engineering, production, and industrial warfare would prove catastrophically wrong. The foundation of Hoffmann's confidence rested on a lifetime of German engineering excellence. Born in 1908 in Stuttgart, the beating heart of German automotive country, he had grown up surrounded by factories that produced some of the world's finest vehicles. His father worked at Daimler-Benz. His grandfather had been a machinist in the pioneering days of German automotive innovation. The family dinner table often featured discussions of metallurgy, tolerances, and the proper way to machine a crankshaft. Engineering wasn't just a profession in the Hoffmann household. It was a philosophy, almost a religion. At 16, young Dieter entered technical school, where instructors drilled into him the principles that defined German manufacturing: precision, craftsmanship, quality over quantity. Every component should be manufactured to exacting tolerances. Every assembly should be checked and rechecked. Every finished product should be built not just to function but to last for decades. This was what separated German engineering from mere manufacturing. Anyone could build something that worked. Germans built things that worked perfectly and endured. He advanced to Engineering University in Munich, where the curriculum reinforced these principles with theoretical rigor. Professors spoke reverently of German engineering integrity, the idea that each component should be manufactured with minimal need for replacement, designed with durability as the primary consideration. Mass production, they taught, was the domain of nations that valued quantity over quality, speed over precision. Germany was built for excellence, others built for adequacy. In 1933, Hoffmann joined Volkswagen as a junior engineer, just as the company was beginning to develop what would become the Volkswagen Beetle. The project embodied everything he had been taught about proper engineering. Ferdinand Porsche's design emphasized elegant simplicity, an air-cooled engine that eliminated the complexity of water cooling systems, lightweight construction that maximized efficiency, a streamlined production process that nonetheless maintained high standards at every stage. When the war began and Volkswagen shifted to military production, Hoffmann moved to the Kübelwagen project, the Wehrmacht's general-purpose military vehicle based on the Beetle platform. The Kübelwagen represented German engineering philosophy applied to military needs. It featured that reliable air-cooled engine, a body designed for ease of repair in field conditions, and a simplicity that German engineers considered the mark of superior design. Unlike vehicles that relied on brute force or redundant systems, the Kübelwagen achieved effectiveness through intelligent engineering. Hoffmann knew the production process intimately. Building a Kübelwagen took time because building it correctly took time. The air-cooled engine required precise manufacturing tolerances. Pistons had to fit exactly within cylinders. Cooling fins had to be precisely shaped for optimal heat dissipation. The body panels needed careful fitting to ensure proper alignment. Each vehicle moved through the factory in distinct stages, engine assembly in one area, where skilled machinists worked with precision tools, chassis construction in another section, where experienced welders ensured structural integrity, body fitting in a third area, where craftsmen adjusted panels for perfect fit, and finally, comprehensive inspection, where quality control engineers examined every system before approving the vehicle for delivery. At peak wartime production, Volkswagen's Wolfsburg plant could produce perhaps 100 Kübelwagens per day. On their best day ever, a record they celebrated as proof of German industrial prowess, they completed 112 vehicles. That figure represented the absolute maximum of what was possible when everything went perfectly. Every worker performing at peak efficiency, every supply delivery arriving on schedule, every component meeting specifications on the first attempt. 112 vehicles in a single day. The plant managers had been proud enough to report it to the Reich Ministry of Armaments. It demonstrated that German engineering could achieve impressive production volumes while maintaining quality standards. The Reich's propaganda reinforced what Hoffmann and his colleagues already believed. Newsreels showed modern German factories with gleaming machinery and dedicated workers producing weapons of superior quality. The Ministry of Propaganda emphasized German technological advantages. Jet aircraft that flew faster than anything the Allies possessed, Tiger tanks with armor that could withstand enemy shells, submarines with advanced snorkel technology that allowed them to remain submerged almost indefinitely. Even as the war turned against Germany, the propaganda insisted that German technological superiority would ultimately overwhelm the Allies' crude numerical advantages. Hoffmann believed it, at least partially. He had toured factories throughout Germany. He had seen the precision of German machine tools, the skill of German machinists, the dedication of German workers. He had witnessed the careful attention to quality that characterized every stage of German manufacturing. When technical reports from the Reich Ministry of Armaments described American industrial production, they emphasized that Americans sacrificed quality for quantity, building mass-produced vehicles with inferior materials, sloppy tolerances, and rushed assembly that resulted in unreliable equipment. The characterization seemed plausible. Americans, after all, were known for their love of mass production, their assembly lines, their emphasis on speed over craftsmanship. German engineers had heard about Henry Ford's production methods, workers performing single, repetitive tasks, vehicles moving continuously through factories, components standardized to the point of interchangeability. To German technical sensibilities, this approach seemed to prioritize efficiency over excellence, quantity over quality, crude effectiveness over engineering integrity. One of Hoffmann's supervisors at Volkswagen had summarized the prevailing view in 1943. Americans build vehicles the way they build everything else: cheaply, quickly, and poorly. They lack our engineering discipline. They sacrifice precision for speed. We build vehicles that last for decades. They build vehicles that barely last for months. One properly engineered German vehicle is worth 3 or 4 of their mass-produced machines. This perspective shaped how German engineers understood the war's industrial dimension. Yes, America had more factories. Yes, American production statistics showed higher numbers of vehicles, aircraft, and weapons. But those numbers, German technical experts assured themselves, didn't account for quality differentials. A German tank built with precision engineering and superior metallurgy could defeat multiple American tanks built with adequate materials and good enough manufacturing. A German aircraft maintained by skilled mechanics could outperform several American aircraft that would break down from shoddy construction. Quality, not quantity, would determine the outcome of industrial warfare. The mathematics seemed compelling. If one German vehicle equaled 3 American vehicles in battlefield effectiveness, then Germany only needed to produce 1/3 as many vehicles to achieve parity. Germany's actual production rates, while lower than American figures, still seemed sufficient when adjusted for this quality multiplier. Producing 100 Kübelwagens per day might not match American numbers, but if each Kübelwagen performed as well as 3 American Jeeps, then Germany was effectively matching American output in practical terms. This calculation rested on assumptions that Hoffmann and his colleagues never questioned. Of course, German engineering produced superior vehicles. Of course, precision manufacturing resulted in better performance. Of course, quality defeated quantity. These weren't merely professional opinions. They were fundamental truths that every aspect of German technical education had reinforced. Questioning them would have been like questioning whether precision engineering was better than sloppy work. The answer seemed self-evident. The Kübelwagen itself seemed to validate this philosophy. German soldiers praised its reliability. Its air-cooled engine eliminated the problems that plagued water-cooled systems in extreme cold. Its lightweight design allowed it to traverse terrain that heavier vehicles struggled with. Its simplicity meant that field mechanics could repair it with basic tools. By German engineering standards, it represented optimal design, a vehicle that achieved effectiveness through intelligent engineering rather than brute force over-engineering. When intelligence reports described American Jeep vehicles, German engineers initially dismissed them as crude improvisations. Four-wheel drive on such a lightweight vehicle seemed unnecessarily complex. More parts meant more potential failures. Water-cooled engines added vulnerability through additional components that could break down. The reported lack of engineering sophistication suggested typical American thinking: build something that works adequately right now, rather than engineering it properly for long-term durability. The Jeep, German engineers concluded, was probably effective enough for American purposes, transporting supplies in rear areas, moving officers between positions, but couldn't match the Kübelwagen's carefully engineered capabilities. Hoffmann's war ended abruptly on a rain-soaked April morning in 1945. American armored units had crossed the Rhine weeks earlier and were driving deep into Germany's industrial heartland. Hoffmann and his engineering team had been evacuating technical documents from the Volkswagen plant blueprints, production records, design specifications when American tanks overran their convoy outside Kassel. The capture itself was almost anticlimactic. One moment they were loading crates into trucks. The next moment, American soldiers with rifles were ordering them to raise their hands. Hoffmann noticed the American vehicles immediately. Jeeps, dozens of them, covered in mud and showing obvious signs of hard use but still running smoothly. They looked crude compared to German military vehicles, simple body panels, minimal aesthetic refinement, functional rather than elegant design. But they worked. Despite their evident age and abuse, they functioned without apparent problems. Engines idled steadily. Transmissions shifted smoothly. These vehicles had clearly travelled hundreds of miles through combat conditions, yet they continued operating. At the POW processing camp, American intelligence officers identified Hoffman and other engineers as high-value technical personnel. Their automotive expertise made them useful for technical assessments and industrial analysis. Within days, they were separated from regular rape prisoners and informed they would be consulting on technical matters related to industrial production. The Americans were polite but firm. The engineers would be traveling to America. They would observe American manufacturing facilities. They would provide technical assessments. Hoffman expected standard interrogation, questions about German factory capacity, vehicle specifications, production bottlenecks, manufacturing techniques. Instead, American intelligence officers asked him about his understanding of American industry. What had German engineers been told about American manufacturing capabilities? What did he personally believe about comparative industrial output between Germany and America? How did he assess the quality difference between German and American vehicles? The questions puzzled him. Why would the Americans care what he thought about their factories? The war was over. Germany was defeated. What difference did his engineering opinions make at this point? Why invest resources in transporting German engineers to America just to tour factories? It seemed like an odd use of victory, showing the defeated enemy your industrial capacity after the fighting had ended. Then, an American intelligence major explained, "We want you to see American production with your own eyes. We want you to measure it, time it, verify it personally. Then we want you to go home and tell other German engineers exactly what you witnessed. We want the truth about American industrial capacity to come from German technical experts, not from Allied propaganda that your people will dismiss." The transport ship from Bremen to New York took 12 days. Hoffman and 6 other German automotive engineers traveled in guarded but relatively comfortable quarters. They were treated as technical consultants rather than prisoners, though they remained under constant supervision. American officers briefed them on what they would witness: average American automotive plants operating at standard wartime production levels. Not showcase facilities, not exceptional examples, just normal factories doing normal work. Hoffman remained skeptical. Every nation engaged in propaganda. The Americans would obviously show them their best facilities, their most modern equipment, their most skilled workers, then claim this represented typical American production. It was what the Reich would have done: showcase excellence, then imply it was universal. Smart propaganda always contained elements of truth presented in misleading contexts. What surprised Hoffman was the Americans' casual, almost dismissive confidence. They didn't boast. They didn't make grand claims about American industrial superiority. They simply stated, matter-of-factly, that he would observe standard assembly procedures at a representative facility. The understated delivery actually increased his curiosity. Why were they so confident? What did they want him to see? The train journey from New York to Toledo took them through America's industrial corridor: Pittsburgh, Cleveland, Akron. Hoffman pressed his face to the train window, mentally counting factories. The scale shocked him. Not the size of individual plants. Germany had large factories, but their density, mile after mile of industrial infrastructure. Plants running continuously, smokestacks everywhere, rail yards packed with freight cars, warehouses stretching to the horizon. In Germany, major factories were concentrated in specific industrial cities, with significant distances between manufacturing centers. Here, industry seemed continuous, almost unbroken across the landscape. "How many factories does America have?" Hoffman asked his American military escort. The lieutenant shrugged casually. "Thousands, maybe tens of thousands, counting smaller facilities. Nobody keeps an exact count." That answer disturbed Hoffman more than boasting would have. The Americans didn't even know precisely how many factories they operated. The number was too large to matter. In Germany, the Reich Ministry of Armaments maintained detailed registries of every significant industrial facility. American industry was apparently so vast that comprehensive accounting was impractical. They arrived in Toledo on a clear spring morning. The Willys Overland plant stretched for blocks, one of the largest automotive facilities Hoffman had ever seen. American workers streamed through the gates for the morning shift. Thousands of them, men and women, black and white, young and old, some barely out of adolescence, others well past what would be considered working age in Germany. The diversity surprised him. In German factories, workers were carefully selected, primarily skilled German men from appropriate backgrounds, supplemented reluctantly during the war by forced labourers from occupied territories. Here, American workers seemed to include anyone physically capable of standing at an assembly line. A stocky American production manager named Robert Henderson greeted the German engineers with surprising friendliness, as if hosting foreign colleagues rather than defeated enemies. "Gentlemen, welcome to our Toledo plant. You're going to observe standard Jeep assembly procedures. We run 3 shifts, 24 hours a day, 7 days a week. Right now we're producing at our normal wartime rate, 1 completed vehicle rolling off the line every 80 seconds. Hoffman performed mental arithmetic. 80 seconds per vehicle meant. He calculated again, certain he had made an error. 45 vehicles per hour. Over 1,000 vehicles per day from a single plant. The numbers seemed impossible. Even accounting for American exaggeration, the claimed production rate exceeded anything Hoffman had encountered in German industry. "Excuse me," Hoffman said carefully in his accented English. 80 seconds for complete vehicle assembly?" Henderson smiled patiently. 80 seconds between finished vehicles rolling off the final station. The actual assembly time from when we start with major components to a running vehicle that can drive under its own power is approximately 15 to 20 minutes, depending on the crew's experience and efficiency. Hoffman looked at his fellow German engineers. Their expressions mirrored his own disbelief. 15 minutes? Absolutely impossible. A properly assembled military vehicle required hours of careful work by skilled craftsmen. This had to be American exaggeration, or perhaps a translation error, or maybe Henderson was describing some preliminary assembly stage rather than complete vehicle construction. "I think," Hoffman said slowly, "there is perhaps a translation problem. You mean 15 hours for complete assembly?" "No, sir," Henderson replied, his tone remaining patient but firm. 15 minutes. From major components to a vehicle that starts, drives, and is ready for delivery. We'll demonstrate the process so you can observe it directly. That's why you're here. That's why we gave you the stopwatch." He gestured toward the factory floor, where the main assembly line stretched into the distance, a continuous mechanical river carrying vehicles in various stages of completion. Workers moved with practiced efficiency at each station, their movements choreographed through repetition. The noise was tremendous: pneumatic wrenches, moving conveyor systems, engines being tested, metal being shaped and fitted. But beneath the cacophony, Hoffman could detect an underlying rhythm, a mechanical precision to the chaos. "Time it yourself if you want," Henderson continued, handing Hoffman a stopwatch. "Start when the frame hits station 1. Stop when the driver starts the engine and drives the vehicle off the line. We have nothing to hide. We want you to verify everything personally." Hoffman looked down at the American stopwatch in his hand, its weight solid and mechanical. His finger hovered over the start button. His entire understanding of industrial production, 12 years of engineering, education, and professional experience, his confidence in German technical superiority, his assumptions about what was physically possible in automotive assembly was about to be tested against observable reality. A bare steel frame appeared on the moving line, carried by the conveyor system towards Station 1. Henderson nodded. "Whenever you're ready, Dr. Hoffman, start timing." Hoffman pressed the button. The stopwatch began counting seconds. And what happened next would change his understanding not just of automotive production, but of industrial warfare, national power, and the fundamental reasons why Germany had lost the war before most Germans even understood what they were fighting against. At Station 1, 2 workers approached the bare frame that had just arrived on the conveyor line. They moved with mechanical precision, no wasted motion, each knowing exactly what to do without verbal communication. 1. The worker positioned himself on the left side of the frame, the other on the right. From overhead racks, pre-assembled front axle components descended on chains. The workers guided the axle into position beneath the frame, then reached for pneumatic wrenches hanging within easy reach. The sound of the pneumatic tools was sharp and rhythmic, a burst of compressed air, the whir of tightening bolts, then silence as the worker moved to the next fastening point. Left side, right side, working simultaneously. Hoffman watched the bolts thread and tighten in seconds. No careful measurement, no individual inspection of each fastening, just rapid, confident installation based on the certainty that components had been manufactured to tolerances that guaranteed proper fitment. The entire front axle installation took perhaps 45 seconds. Then the frame moved forward on the conveyor, already travelling towards Station 2 before the workers at Station 1 had even returned their tools to the hanging racks. Station 2 handled engine installation, a complete engine already fully assembled, tested, and ready for mounting descended from an overhead hoist system. 4 workers converged on it simultaneously, 2 guiding the engine into position, while the other 2 prepared the mounting points on the frame. The engine was substantial, a water-cooled unit that must have weighed several hundred pounds, yet the workers manoeuvred it with practiced ease using the mechanical advantage of the hoist system. More pneumatic wrenches. The engine bolted to its mounts in less than 90 seconds. Hoffman's engineering mind automatically catalogued what he was seeing. The engine arrived as a complete, tested module, not as components to be assembled on the line. Someone somewhere had built that engine, tested it, verified it, met specifications, then delivered it to final assembly ready for installation. The assembly line workers weren't building engines, they were installing pre-built, pre-tested units. The frame moved forward. Station 3, transmission installation. Again, a complete pre-assembled unit descended from overhead. Again, workers guided it into position with economical movements. Again, pneumatic tools secured it in place in under 2 minutes. The pattern was becoming clear. Everything was modular. Everything was pre-assembled. The final assembly line simply connected major systems together. Hoffman glanced at his stopwatch. 3 minutes had elapsed. The vehicle now had a front axle, engine, and transmission. In a German factory, installing just the engine would typically take an experienced mechanic 15 to 20 minutes of careful work, ensuring proper alignment, verifying all mounting points, checking clearances. Here, 4 workers had installed 3 major systems in 3 minutes. Station 4 brought body installation. The distinctive Jeep body already completely painted, already fitted with all necessary brackets and mounting points descended from another overhead system. It was a single piece, the entire passenger compartment and hood section manufactured and finished as a unit. 6 workers positioned it onto the chassis, 4 holding it steady while 2 secured the mounting bolts. The body settled onto the frame with a precision that suggested extremely tight manufacturing tolerances. No shimming, no adjustment, no custom fitting. It simply fit, perfectly, the first time. Hoffman heard one of his fellow German engineers mutter something in German. He glanced over. The man's face showed the same mixture of disbelief and dawning horror that Hoffman himself felt. They were watching something that shouldn't be possible, according to everything they had been taught about proper manufacturing. Station 5 installed the electrical system, but it wasn't individual wires being routed through the vehicle. It was a pre-assembled wiring harness, every wire already cut to exact length, every connection already terminated, the entire electrical system manufactured as a single plug-and-play unit. Workers simply laid the harness into pre-designed routing channels in the body, then connected a series of quick disconnect plugs. Dashboard instruments, plug in. Headlights, plug in. Starter system, plug in. The entire electrical system installation took perhaps 90 seconds. Station 6, wheels and tires. They arrived already mounted and balanced, pre-assembled units that workers simply bolted onto the hubs. All 4 wheels installed in less than 60 seconds, 2 workers per side working simultaneously. Hoffman checked his stopwatch again. 7 minutes had elapsed. The Jeep was recognizable now, nearly complete. A functional military vehicle was taking shape before his eyes at a speed that seemed to violate physical laws of manufacturing. Station 7 handled the fuel system. The fuel tank, already fitted with all necessary brackets and fuel lines, dropped into its designated space. Workers secured it, connected the fuel lines to the engine using quick connect fittings that required no tools, then added fuel from a measured dispensing system. The entire process took perhaps 45 seconds. Station 8 dealt with the cooling system. The radiator had been installed with the engine, so this station simply filled it with coolant, connected the overflow reservoir, and verified that all cooling system hoses were properly secured. Another 60 seconds. Station 9 completed final connections, drive belts, remaining hoses, small components that hadn't been part of the major sub-assemblies. Workers moved with the confidence of people who had performed these exact tasks thousands of times, their hands finding the right tools and components without conscious thought. Station 10 verified fluid levels. A single worker with a checklist walked around the vehicle, checking oil level, coolant level, transmission fluid, brake fluid. He made check marks on a form attached to a clipboard, his inspection taking perhaps 30 seconds. Station 11 brought the first real inspection. A quality control inspector, an older man wearing a different colored uniform that identified his supervisory role, walked completely around the vehicle, checking connections, testing lights, verifying that all assembly steps had been completed correctly. He tugged on several bolted connections, checked that the steering wheel turned freely, verified that the brake pedal had appropriate resistance, examined the body panel alignments. His inspection was thorough but rapid, the practiced assessment of someone who knew exactly what to look for and could identify problems at a glance. 12 minutes had elapsed on Hoffman's stopwatch. 12 minutes from bare frame to apparently complete vehicle. Then came the moment that would haunt Hoffman's memory for the rest of his life. At Station 12, a driver, a young man who looked barely 20 years old, climbed into the seat. He adjusted the mirror with a casual gesture, checked the gauges on the dashboard, then turned the ignition key. The engine started immediately. No hesitation, no coughing, no need for adjustment or warm-up. The engine caught on the first attempt and settled into a smooth, steady idle. The young driver let it run for perhaps 10 seconds, listening to the engine note, watching the gauges, then releasing the parking brake. He depressed the clutch, shifted into first gear with a smooth motion, released the clutch, and applied gentle throttle. The Jeep rolled forward under its own power. The driver guided it off the assembly line, turned it toward the parking area, shifted through the gears, and drove away as if he were simply moving a vehicle that had been sitting in storage rather than one that had been assembled from bare components 14 minutes earlier. Hoffman pressed the stop button on his stopwatch. The mechanical clicking seemed impossibly loud despite the factory noise surrounding him. 14 minutes, 37 seconds. He stared at the stopped watch, then at Henderson, then back at the watch, as if the numbers might change if he looked away and back again. 14 minutes and 37 seconds from bare frame to running vehicle. Not a partially assembled vehicle needing additional work, not a vehicle requiring break-in or adjustment, a completed military vehicle that had just driven away under its own power. This is, Hoffman struggled to find words. This is normal production? That crew was actually a bit slow today, Henderson said with casual matter-of-factness. Good experienced crews regularly do it in 13 to 14 minutes. We had one team hit 11 minutes and 48 seconds last month, but that was with everything going perfectly. No delays, no minor issues, components arriving at exactly the right moments. Hoffman felt something fundamental shift inside his understanding of reality. Not just a surprise, Not mere shock at an unexpected capability, something deeper. A comprehensive recalculation of everything he thought he understood about industrial production, national power, and the war his country had just lost. How many? Hoffman asked, his voice barely audible over the factory noise. How many vehicles per day does this plant produce? Henderson checked a clipboard hanging on a nearby post. From this facility specifically, we're currently averaging 1,100 completed units per day. That's 45 to 46 per hour across all 3 shifts, 24 hours a day, 7 days a week. We've been running this pace since the early 1943, 1,100 vehicles per day, from a single factory. Hoffman performed the arithmetic with the mechanical precision of someone whose mind was operating on training and habit, while his consciousness reeled from implications. 1,100 per day meant 7,700 per week, over 30,000 per month, more than 360,000 per year from this one facility alone. And there are other plants? Hoffman heard himself ask, his voice sounding distant and strange in his own ears. Other factories producing Jeeps? 2 primary production facilities, Henderson confirmed, consulting his clipboard. We're the main producer here at Willys Overland in Toledo. Ford Motor Company also manufactures them under license at their facility in Michigan. Between both plants, combined production is currently running about 2,000 Jeeps per day. That's actually down from peak production. We've been ramping down slightly since Germany surrendered. At maximum wartime output, we were doing somewhat higher numbers. 2,000 per day. Hoffman's mind translated the number into terms he could comprehend. 14,000 per week. 60,000 per month. Over 700,000 per year at current reduced production rates. Higher at peak. He thought about Volkswagen's Kübelwagen production. Their best day ever, the plant record they had celebrated as proof of German industrial capability, had been 112 vehicles. On an exceptional day, with everything going perfectly, Volkswagen had produced 112 Kübelwagens and considered it a triumph worth reporting to the Reich Ministry of Armaments. The Americans produced more vehicles in 90 minutes than Volkswagen produced in its best day ever. One of Hoffman's fellow engineers spoke quietly in German, doing his own calculations. The Kübelwagen, we produced approximately 52,000 units during the entire war, 5 years of continuous production at maximum capacity. Another engineer responded, also in German, his voice hollow. At 2,000 per day, they produced that quantity in 26 days. Henderson, who apparently understood at least some German, smiled thinly. Actually, total wartime Jeep production reached approximately 647,000 units across all variants from both manufacturers. Production began in mid-1941 and ran through the present. Just under 4 years of manufacturing, 647,000 Jeeps, against Germany's 52,000 Kübelwagens, a production ratio of more than 12 to 1. The Americans had manufactured 12 vehicles for every one that Germany produced, and they had done it faster, in less total time, with what appeared to be far less skilled labor performing the actual assembly work. The numbers were devastating, not because they were close. Close numbers could be explained by marginal differences in efficiency or resources. These numbers represented a categorical difference in industrial capacity. This wasn't a competition between comparable manufacturing powers. This was a demonstration that Germany and America had never been competing in the same industrial weight class at all. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Henderson walked them along the assembly line, pointing out details that Hoffman had missed during his initial shocked observation. The key to the entire system is interchangeability, Henderson explained, his tone taking on the quality of an engineer discussing technical specifications with colleagues. Every component manufactured for Jeep assembly fits every vehicle without adjustment. No custom fitting, no individual modification. Parts are manufactured to tolerances that absolutely guarantee correct fitment. He reached into a nearby parts bin and pulled out a steering wheel. This steering wheel will fit every single Jeep we manufacture. No filing, no adjustment, no custom work required. The same principle applies to every other component in the vehicle. Every bolt, every bracket, every wire, every mechanical part. Complete interchangeability across the entire production run, across both manufacturing facilities, across all 4 years of production. To Hoffman, this seemed to violate fundamental principles of quality manufacturing. German engineering emphasized precision through custom-fitting manufacturing components slightly oversized or with tolerance ranges that allowed skilled workers to adjust each part during assembly for perfect fitment. It ensured quality, guaranteed proper function, and required skilled craftsmen who understood how to achieve proper fit through careful adjustment. The American approach eliminated skilled assembly labor almost entirely. If every component fit every vehicle without adjustment, assembly didn't require craftsmen. It required workers who could operate pneumatic wrenches and follow standardized procedures. The assembly line workers he had observed weren't skilled automotive mechanics. They were people who had learned a specific, limited task and could perform it rapidly through repetition. Field maintenance? Hoffman asked, his engineering mind immediately considering the implications for repair and logistics. Replacement parts in combat zones? Any part fits any Jeep ever manufactured, Henderson confirmed. A transmission built here in Toledo today will fit perfectly in a Jeep we manufactured in 1942. Same mounting points, same connections, same specifications, guaranteed compatibility. We've produced millions of spare parts. Every theater of operations has access to complete replacement component inventories. Transmission fails. Replace it with any transmission from stock. Engine damaged. Replace it with any engine. Axle breaks. Any axle will fit. This explained something Hoffman had observed during the final months of the war. Captured American vehicles, even severely damaged ones, somehow remained operational longer than seemed possible. German mechanics had marveled at how easy American vehicles were to repair, how quickly they could be returned to service, even after significant damage. Now Hoffman understood why. Complete interchangeability meant any part from any vehicle could replace any damaged component without modification. American vehicles weren't necessarily more durable than German vehicles, they were infinitely more repairable. German vehicles required specific parts, often custom-fitted during original assembly. If a specialized component was damaged and replacement parts weren't available, the entire vehicle became inoperable. In a war of attrition, with supply lines stretched and logistics strained, that difference between American interchangeability and German specificity meant American vehicles stayed operational while German vehicles became immobile scrap for want of a single unavailable custom part. Henderson introduced them to several assembly line workers during the mid-morning break period. Hoffman asked about their training, genuinely curious how long it took to develop the skills he had observed. "I've been working on here for about 6 months," one woman said. She appeared perhaps 25 years old, wearing work clothes and with her hair tied back in a practical style. "It took me approximately 2 weeks to learn my station. Now I can install a transmission assembly faster than anyone else on my shift." 2 weeks. At Volkswagen, automotive assembly workers underwent months of training in basic mechanical principles before even beginning factory floor work. Even after initial training, new workers started on simple tasks and gradually advanced to complex assembly work over a period of years as they gained experience and demonstrated competence. Transmission installation was considered skilled labor requiring extensive mechanical knowledge. "Before taking this job," another worker added, a young man who looked perhaps 30, "I worked at a grocery store, never touched an automotive vehicle in my life beyond driving one. Now I'm part of the engine installation team." Hoffman struggled to process this information. grocery clerks installing engines, women with 2 weeks of training mounting transmissions, people with no automotive background whatsoever assembling military vehicles. According to everything he had been taught about manufacturing, this should produce inferior results. Vehicles assembled by unskilled workers should be unreliable, poorly constructed, prone to failure. But he had watched the Jeep drive off the assembly line. The engine had started immediately. The vehicle had moved smoothly. The quality appeared entirely adequate for military use. The inspector's examination had found no issues requiring correction. That word adequate suddenly seemed central to understanding what he was witnessing. German engineering sought excellence. American manufacturing aimed for adequacy. But adequate, produced in overwhelming quantity, defeated excellent produced in limited numbers. 1,000 adequate vehicles overwhelmed 100 excellent vehicles through simple arithmetic. Quality advantages became strategically irrelevant when the quantity differential reached 12-1. The secret, Henderson said, noticing Hoffman's troubled expression, isn't worker skill. The secret is process design. We engineer the manufacturing process so thoroughly that minimal worker training produces consistent results. Every station has detailed written procedures. Every tool is specifically designed for its precise task. Every component is engineered for ease of installation. We systematically remove skill requirements through superior process engineering. This represented an industrial philosophy that Hoffman had never encountered in German manufacturing. German engineers focused on producing superior components, then relied on skilled workers to assemble those components carefully using traditional craftsmanship. American engineers designed manufacturing processes that allowed minimally trained workers to assemble adequate components rapidly, using specially designed tools and procedures. Different fundamental goals, different core methodologies, but both approaches produced the same end result, a functional military vehicle that could transport soldiers and supplies, except the American methodology produced that functional vehicle 12 times faster and in quantities 12 times larger than the German approach. Henderson led them to the receiving area where raw components arrived at the factory. Railroad freight cars lined the loading docks, dozens of them in various stages of unloading, a continuous stream of supplies feeding the insatiable assembly line. Forklifts moved constantly, workers guided pallets of components. The entire logistics operation hummed with mechanical efficiency. We receive approximately 15,000 major components every single day, Henderson explained, gesturing at the organized chaos of the loading area. Engines, transmissions, axles, body assemblies, electrical systems, wheels, hundreds of smaller components, all manufactured at other facilities, shipped here for final assembly. Where? Hoffman asked, needing to understand the scope of the supply network. Where are these components manufactured? Henderson consulted a thick logistics binder filled with supplier information. Engines come from 7 different plants across 4 states: Michigan, Ohio, Indiana, and Wisconsin. Transmissions from 5 separate plants, axles from 6 different facilities, body stampings from 11 plants across the Midwest and Northeast, electrical harnesses from 3 specialized suppliers. We coordinate supply deliveries from over 200 component suppliers in total. 200 suppliers, 7 engine plants, 11 body stamping facilities. The Americans hadn't simply built a few large factories. They had constructed an entire distributed manufacturing ecosystem spanning multiple states, coordinated through logistics networks of staggering complexity. A single vehicle type had production infrastructure distributed across thousands of miles, with rail systems, communication networks, and inventory management systems coordinating the flow of millions of components. Hoffman thought about Volkswagen's supply chain. Most components were manufactured in Wolfsburg or in nearby regional facilities. Suppliers were concentrated in northern Germany, often within 100 kilometers of the main plant. When Allied bombing disrupted a supplier, production at Wolfsburg stopped. When transportation networks were damaged, components couldn't reach the assembly plant. The entire system was fragile, vulnerable, and concentrated. The American system had redundancy at every level. If one supplier failed, 6 others continued producing engines. If one plant was damaged, though no American production facilities faced any threat of enemy action, production shifted to other locations. Distributed manufacturing meant distributed resilience. The system was designed to be nearly impossible to disrupt because no single point of failure could stop production. And the logistics infrastructure required to coordinate this complexity, the railroad systems moving millions of tons of components, the communication networks tracking inventory and shipments, the management systems ensuring the right parts arrived at the right factories at the right times, represented industrial sophistication that German manufacturing had never approached. Standing in the receiving area, watching freight cars being unloaded with mechanical efficiency, Hoffmann experienced a moment of clarity that felt almost spiritual in its intensity and horror. Germany had lost the war in 1941. They simply hadn't known it yet. Not at Stalingrad, though that battle was catastrophic. Not in North Africa, though that campaign failed. Not when the Allies landed at Normandy, though that invasion sealed Germany's fate. Germany had lost the war the moment America entered it, because American industrial capacity made German victory mathematically impossible, regardless of battlefield performance. The Wehrmacht could win tactical battles. German engineering could produce superior weapons. German soldiers could fight with extraordinary skill and courage. German generals could demonstrate brilliant operational art. None of it mattered, none of it could possibly matter against industrial production that measured in millions while German output measured in thousands. He thought about the propaganda films he had watched during the war. German factories producing tanks, aircraft, submarines. The newsreels made it look impressive, showing modern facilities with dedicated workers building weapons by the dozens. German production of 50 tanks per day had seemed substantial. 100 aircraft per week appeared significant, but America produced thousands of vehicles per day, tens of thousands per week, hundreds of thousands per month. The scale difference wasn't marginal. It wasn't a matter of German factories being somewhat less productive than American ones. The differential was categorical, fundamental, absolute. Germany and America weren't competing in the same industrial weight class. It was like comparing a master craftsman's workshop to a continent-spanning industrial machine. "Your face?" Henderson said quietly, observing Hoffmann's expression. "You understand now, don't you?" Hoffmann nodded slowly, unable to articulate the full weight of what he was processing. "We never had a chance." "No," Henderson agreed, his tone not triumphant but matter-of-fact, almost sympathetic. "You didn't. Not against this." He gestured at the factory floor, where another Jeep was already moving down the assembly line, another vehicle being born from the mechanical rhythm of American mass production. Henderson continued the tour, showing them other areas of the plant that Hoffmann had not yet seen. The sub-assembly building, where engines were constructed not one at a time but on dedicated production lines that manufactured hundreds per day. The stamping facility, where body panels emerged from massive presses at a rate of one every few seconds, sheets of steel transformed into shaped components through mechanical force and precision dies. The paint facility, where body assemblies moved through automated spray booths, emerging painted and dried in minutes rather than the hours required by traditional painting methods. Everything was mechanized. Everything was continuous. Everything was designed for speed and volume over craftsmanship and individual precision. The American industrial philosophy was apparent in every system. Remove human variability through mechanical consistency. Eliminate skill requirements through process design, achieve quality through statistical reliability rather than individual inspection. They visited the quality control area and Hoffman expected to find extensive inspection processes, teams of experienced inspectors examining every vehicle thoroughly. Instead, he found statistical sampling. Randomly selected vehicles were tested exhaustively, every system checked, every component verified, performance measured against specifications. But the assumption underlying the process was that consistent manufacturing procedures produced consistent results. German quality control inspected every vehicle individually because German manufacturing assumed variability that required verification. American quality control trusted the process and verified it through sampling. It was heretical to German engineering principles. It was also vastly more efficient, allowing the quality control staff to focus intensive inspection on representative samples rather than superficial inspection on every unit. The outdoor storage yards held thousands of completed Jeeps awaiting shipment to ports for transport overseas. Row after row of identical vehicles, parked in organized lots, ready for delivery to Europe or the Pacific Theatre. The scale was numbing. This represented perhaps 2 or 3 days of production from this single plant. Tomorrow will produce another 1,000. The day after would produce another 1,000. Continuous, relentless, overwhelming production that never stopped, never slowed, never faltered. We're actually ramping down current production, Henderson mentioned casually. Now that Germany has surrendered, and with the Pacific War appearing to be approaching its conclusion, we're transitioning toward peacetime production levels. At peak wartime output, we were doing considerably more than current numbers. Ramping down, American industry could reduce production and still exceed German maximum capacity by enormous margins. The casual mention of transitioning to peacetime drove home a point Hoffman hadn't fully processed. American industry had converted to war production temporarily. These factories had existed before the war, producing civilian vehicles. They had shifted to military production when needed. After the war ended, they would shift back to civilian production. Germany's wartime factories were purpose-built for military manufacturing. When the war ended, they had no peacetime application, no civilian market to serve, no economic justification for continued operation. American factories could pivot seamlessly between war and peace, between military and civilian production. German factories were specialized tools that became obsolete the moment the fighting stopped. As they prepared to leave the plant at the end of the tour, Henderson asked if the German engineers had any final questions. Hoffman had one question that had been forming in his mind throughout the day. Why? Why show us this now? The war is over. Germany is defeated. What purpose does this demonstration serve? Henderson considered the question carefully before responding. 2 reasons, Dr. Hoffman. First reason, so you understand exactly why you lost. Not because German engineering was inferior. Your Kubelwagen is actually a better designed vehicle than our Jeep in several respects. Better suited for certain terrain, more fuel efficient, simpler to maintain in some ways. You lost because industrial capacity determines modern warfare, and you never had any realistic chance against American industrial production. We want you to understand that completely. He paused, looking out at the factory floor where the assembly line continued its endless progression, another Jeep taking shape even as they spoke. Second reason, so you go home and tell people, tell German engineers, tell German industrialists, tell German military officers, tell anyone who will listen. Tell them exactly what American industrial capacity looks like, what it can produce, how it operates. We want the testimony to come from German technical experts, not from American propaganda that your people will dismiss as exaggeration. We want you to be witnesses who can verify everything personally, who can answer technical questions, who can provide engineering-level detail that other German engineers will have to take seriously. Henderson's expression became grave. We want you to tell this story so that no nation ever makes the mistake of fighting America again while believing they can match American production. Quality doesn't beat quantity when the quantity difference is 12 to 1. Technical superiority doesn't overcome industrial capacity when the capacity difference is measured in millions versus thousands. We want this lesson learned so thoroughly that it never needs to be taught again through war. Hoffman understood. He was being sent home as a messenger, an evangelist of industrial reality, a witness who had seen American manufacturing capacity firsthand and could testify to its scale with the credibility of a trained engineer. The Americans wanted the truth about industrial warfare to spread through German technical communities not as propaganda, but as verified testimony from credible sources. He would fulfill that role for the rest of his life, though the burden of that truth would weigh on him constantly. The return journey to Germany carried a group of engineers whose understanding of industrial reality had been fundamentally shattered. They barely spoke during the train ride back to New York, each man processing what he had witnessed in isolation. Hoffman stared out the window at the American industrial landscape, passing by factory after factory after factory, a seemingly endless infrastructure of manufacturing capacity stretching across the continent. He filled his notebook with calculations. If Toledo produced 1,100 Jeeps daily and Ford's Michigan plant produced similar numbers, that meant approximately 2,000 Jeeps per day. Multiply by 365 days, more than 700,000 per year at current reduced rates, against Germany's total Kugelwagen production of 52,000 over 5 years. He calculated further, estimating relative investment. If production costs per vehicle were roughly comparable and the speed of American assembly suggested their costs were actually lower, then America had invested more than 12 times the resources into a single vehicle category compared to Germany's entire general-purpose vehicle production. And Jeeps were just one vehicle type, one category among dozens. The Americans also produced trucks by the hundreds of thousands, tanks by the tens of thousands, aircraft by the scores of thousands, ships by the thousands, all at similar proportional scales compared to German production. The mathematical reality of industrial defeat became inescapable. At the prisoner processing center in New Jersey, awaiting transport back to Germany, Hoffman and his fellow engineers discussed what they had witnessed. The conversations oscillated between technical analysis and something approaching existential despair. Process engineering, one engineer said with reluctant admiration. They completely eliminated skill requirements from assembly work. Anyone can work that line after minimal training. That's the genius of their approach, another replied. They didn't need skilled automotive workers. They just needed workers, any workers. And America had unlimited labor that could be mobilized without affecting national security. Women, minorities, older workers, young workers, everyone could contribute to production. Germany couldn't do that. We needed skilled German men, but those men were needed for military service. America could put literally anyone on an assembly line and achieve adequate results. It's not just labor availability, Hoffman interjected. It's the entire industrial ecosystem, distributed supply chains spanning multiple states, redundant manufacturing capacity at every level, statistical quality control instead of individual inspection, modular components with guaranteed interchangeability. They designed their entire industrial system for maximum scale, not for precision or craftsmanship. A third engineer added quietly, "We were building watches. They were building hammers. We thought precision would win. But in industrial warfare, you don't need a perfect weapon. You need 10,000 adequate weapons against the enemy's 1,000 perfect weapons." The room fell into heavy silence as the implications settled over them. American intelligence officers debriefed each engineer separately, asking detailed questions about their observations and technical assessments. Hoffman's interviewer, an army major named Barrett, took extensive notes throughout the conversation. "In your professional opinion, Dr. Hoffman, how does German automotive production compare to what you observed at the Toledo facility?" Hoffman chose his words with care. There is no meaningful comparison possible. The scale difference is too large for comparative analysis. It would be like comparing a village bakery to a continental industrial bread factory. Both produce bread, but beyond that basic similarity, they operate according to entirely different principles and achieve entirely different outputs. Did you observe any American production techniques that German industry could have adopted to improve efficiency? All of them, and none of them. Major Barrett raised an eyebrow. Please explain that apparent contradiction. All of them, every technique we observed would theoretically improve production efficiency. Interchangeable components manufactured to guaranteed tolerances. Sub-assembly processes with parallel production streams. Simplified station tasks requiring minimal training. Statistical quality control instead of individual inspection. All of these represent superior methodologies for achieving mass production. Hoffman paused, organizing his thoughts. And none of them because these techniques require an industrial infrastructure that Germany doesn't possess and couldn't have built. Distributed supply chains require extensive transportation networks that can operate without threat of disruption. Sub-assembly processes require multiple coordinated facilities with reliable logistics between them. True interchangeability requires precision manufacturing capability at enormous scale across hundreds of suppliers. American methodology fundamentally assumes unlimited resources, secure production facilities, and continental-scale infrastructure. German methodology adapted to resource constraints, vulnerability to bombing, and limited geographic scope. He met Major Barrett's eyes directly. America designed an industrial system optimized for a resource-rich continent with production facilities completely secure from enemy action. Germany designed an industrial system for a resource-poor nation under constant aerial bombardment with supply lines vulnerable to interdiction. Your methodology is superior because your circumstances are superior. We couldn't have built what you built even if we had fully understood the principles, because we lacked the fundamental preconditions that make your system possible. Major Barrett made detailed notes, then asked one final question. If German leadership had possessed accurate intelligence about American production capacity before the war began, would it have changed German strategic calculations? Hoffman laughed bitterly, a sound without humor. If German leadership had truly understood what I witnessed in Toledo, the war would never have started. No rational person would choose to fight a nation that can produce military vehicles in 15 minutes, when your own nation requires hours. The production differential is simply too large to overcome through any conceivable military advantage. Superior tactics cannot compensate for 12-to-1 industrial inferiority. Better engineering cannot overcome million to thousand production ratios. So, Germany's defeat was inevitable from the moment America entered the war. Germany's defeat was inevitable from the moment German leadership failed to understand what fighting America actually meant. Hoffman replied, "We weren't fighting just another nation. We were fighting an industrial capacity that no military force could overcome. We fought brilliantly and lost mathematically." Major Barrett closed his notebook. "One more question, Dr. Hoffman. When you return to Germany and tell people what you witnessed, do you believe they'll accept your testimony?" This question troubled Hoffman deeply because he had been considering it throughout the journey. "That's my greatest concern, Major. I have witnessed American industrial capacity firsthand. I personally timed the Jeep assembly. I can verify every detail, provide engineering-level specifications, answer technical questions. I have documentation and photographs. I can testify to everything with absolute certainty." He paused, and his expression troubled. "And I believe most Germans will dismiss my testimony as American propaganda or defeatist thinking. German propaganda spent years telling us that German industry was superior, that German engineering was unmatched, that American products were inferior. Those beliefs are deeply embedded in German professional culture, especially among engineers who built their identities around German technical superiority. My testimony contradicts fundamental assumptions that people have held as unquestionable truths. Claims that Americans assemble vehicles in 15 minutes will seem too extreme to be credible. Statistics showing 12-to-1 production ratios will be dismissed as exaggerations. Even detailed technical testimony from trained engineers will be rejected by people who cannot psychologically accept that everything they believed about German industrial superiority was fundamentally wrong. Major Barrett nodded slowly. That's exactly why we brought you here, Dr. Hoffman. We need multiple German engineers telling the same story, providing corroborating testimony, answering technical challenges from skeptics. The truth needs to come from enough credible German sources that dismissal becomes impossible. The transport ship brought them back to a Germany that barely resembled the nation they had left. Cities lay in ruins. Factories were destroyed or damaged beyond immediate repair. The industrial infrastructure that had taken decades to build was reduced to rubble in many areas. Volkswagen's Wolfsburg plant had been bombed repeatedly. The facility where Hoffman had spent 12 years of his career was partially demolished. The irony wasn't lost on Hoffman. Germany's limited industrial capacity had been systematically destroyed through strategic bombing. But even if every German factory had survived intact and operated at absolute peak efficiency, Germany still couldn't have matched American production. The bombing had merely destroyed what was already inadequate. He found his family in Stuttgart. His wife and 2 daughters had survived, though their home was damaged. He found employment almost immediately. Occupied Germany desperately needed engineers to plan reconstruction, and the American military authorities particularly valued automotive engineers who could help restart civilian production. Hoffman spent the following months working on reconstruction plans, but his mind kept returning to Toledo, to the assembly line, to the 15-minute Jeep, to the mathematical certainty of industrial defeat. He began giving presentations to engineering societies, reconstruction planning committees, and industrial groups. He described American production methods in precise technical detail. He explained the philosophy of mass production over precision craftsmanship. He shared his calculations about production differentials and their strategic implications. He showed the stopwatch, still keeping accurate time, and described exactly what he had measured. The reactions varied considerably. Some engineers listened intently, asked detailed technical questions, and absorbed the implications with visible distress. Others became defensive, arguing that German engineering remained superior in quality, even if inferior in quantity. A few were openly hostile, suggesting that Hoffman had been psychologically broken by captivity or was deliberately undermining German professional pride. "You're claiming German engineering was inferior?" One engineer challenged during a presentation in Munich, his tone aggressive. "No," Hoffman replied with careful precision. "I'm stating that German engineering optimized for the wrong strategic goal. We optimized for quality, precision, durability, and craftsmanship. Americans optimized for scale, speed, simplicity, and volume. In industrial warfare, scale defeats precision. We built superior vehicles as individual products. They built adequate vehicles in overwhelming numbers. Adequate, multiplied by overwhelming numbers, defeats superior multiplied by limited numbers. Mathematics is inescapable. But that's merely a resource question," the challenger argued. "If Germany had possessed America's resources, our superior engineering would have produced even greater output." Hoffman shook his head firmly. "That's the critical mistake in thinking. American mass production isn't just about resource availability. It's about fundamental methodology process engineering that eliminates skill requirements, interchangeability that enables unskilled assembly, distributed manufacturing that creates resilience, statistical quality control that achieves reliability through process consistency rather than individual inspection. Even with equal resources, American methodology produces vastly greater output because the entire system is architected for maximum scale." These debates became familiar over the following months and years. German engineers struggled to canonize, accept that their fundamental approach had been strategically flawed. It was psychologically easier to blame resource scarcity than to question core methodology and professional philosophy. Over subsequent years, as more German engineers toured American facilities during the occupation period and confirmed Hoffmann's observations, his testimony gained credibility. The Allied authorities actively encouraged these exchanges, wanting German industry to adopt American production methods for post-war reconstruction. The economic benefits were obvious. Mass production techniques would allow Germany to rebuild more quickly and efficiently. Gradually, reluctantly, German automotive engineering began shifting. Volkswagen, restarting civilian production under Allied supervision, incorporated American mass production techniques while maintaining German attention to engineering quality where it added genuine value. Mercedes-Benz studied American assembly methods and adapted them for German conditions. BMW restructured their manufacturing processes. German industry slowly acknowledged that mass production required a different engineering philosophy than traditional craftsmanship. But the lesson extended far beyond automotive production. German strategic thinking had to grapple with the uncomfortable reality that industrial capacity determined modern warfare outcomes more decisively than tactical excellence, weapon quality, or soldier skill. The Wehrmacht had been one of history's most effective fighting forces. German weapons were often technically superior to Allied equivalents. German tactics were innovative and sophisticated. German soldiers were skilled and courageous. None of it had mattered against industrial output that measured in millions, while German production measured in thousands. Quality, courage, and skill couldn't overcome mathematical impossibility. Industrial capacity had determined the war's outcome before the first shots were fired, and Germany had never possessed any realistic path to victory once America entered the conflict. Hoffmann carried the weight of this knowledge for the remainder of his life. He had believed deeply in German engineering superiority. He had spent 12 years at Volkswagen perfecting German automotive production methods. He had taken professional pride in precision, craftsmanship, and quality. His entire professional identity was built on these principles. Then he had watched Americans assemble a vehicle in 15 minutes and understood that everything he believed about industrial engineering was strategically irrelevant. Excellence didn't matter when adequate could be produced in overwhelming quantity. Precision didn't matter when simplicity enabled 12 times greater output. Craftsmanship didn't matter when process engineering eliminated the need for craftsmen. The psychological burden was profound. His wife later told interviewers that he would sometimes sit silently for hours, staring at nothing, lost in thoughts about what he had witnessed in Toledo. The stopwatch he had used to time the Jeep assembly, he kept it in his desk drawer, taking it out occasionally to verify that his memories were accurate, that the numbers were real, that he hadn't imagined or misremembered the 15 minutes that changed his understanding of everything. He struggled with depression during the post-war years. Part of him wished he had never seen the Toledo plant, never measured the assembly time, never understood the full scope of German industrial inadequacy. Ignorance might have been more comfortable than knowledge, but he couldn't unknow what he had learned, couldn't unsee what he had witnessed, couldn't escape the mathematical certainty of industrial defeat. The final irony of Hoffmann's story only became fully apparent decades later. Volkswagen, the company where he had worked during the war, eventually became one of the world's largest automotive manufacturers by adopting and adapting the American mass production techniques that Hoffmann had witnessed and initially struggled to accept. The Volkswagen Beetle, produced from the late 1940s through 2003, became one of history's most successful vehicles with over 21 million units manufactured globally. Its success came not from traditional German precision engineering alone, but from mass production methods scaled globally, the same industrial philosophy Hoffmann had seen demonstrated with the Jeep. German automotive engineering didn't die after the war. It transformed, incorporating American mass production methodology while maintaining German quality standards where they genuinely added value rather than merely slowing production. The synthesis German precision applied within American-style mass production systems created the foundation of the modern German automotive industry that would eventually dominate global markets. But achieving that synthesis required German engineers to admit that their pre-war methodology had been strategically inadequate. It required accepting that American industrial philosophy, which they had dismissed as crude quality sacrificing, was actually superior for large-scale production. It required professional humility about technical assumptions they had held as absolute truths. Hoffmann gave his final public presentation in 1968 at an automotive engineering conference in Frankfurt. He was 60 years old, still working as a consultant for Volkswagen, still carrying the burden of what he had witnessed 23 years earlier. His presentation topic, Industrial Philosophy and Strategic Consequences, Lessons from American Automotive Production. He described his experience in Toledo, the memories still vivid despite more than 2 decades passing. He displayed the stopwatch, now worn and aged but still functional. He walked the audience through the 15-minute assembly process that had changed his understanding of industrial engineering and national power. "I tell this story," he concluded, his voice carrying the weight of hard-earned wisdom, "not to glorify American industry or diminish German engineering capability. I tell it so that engineers understand that technical excellence must serve strategic goals, not exist for its own sake. We Germans built exceptional vehicles with precision and care. Americans built adequate vehicles with speed and overwhelming scale. In war, scale won. Superior quality could not overcome 12-to-1 quantity differences." He held up the worn stopwatch, its mechanism still clicking with mechanical precision. 15 minutes. That's how long American workers needed to assemble a vehicle that helped win the war. We needed hours to build vehicles that fought bravely but lost mathematically. The lesson isn't that fast assembly is inherently better than careful construction. The lesson is that adequate quality, produced in overwhelming quantities, defeats excellent quality produced in limited numbers. This is the fundamental mathematics of industrial warfare. Modern engineering must remember this lesson. Industrial capacity determines possible strategic outcomes. Technical superiority within inadequate production scale is strategic failure. America didn't win the war through better engineering. America won through better industrial philosophy applied at continental scale with unlimited resources and absolute security. We must learn from defeat, or we learn nothing at all. Dieter Hoffmann died in 1973 at age 65. His obituary in German automotive trade publications mentioned his career at Volkswagen, his contributions to post-war reconstruction, and his role as an educator who trained a new generation of German engineers in modern production methods. It didn't specifically mention the 15 minutes in Toledo that had defined his later life and thinking, but that story lived on in the memories of engineers he had taught, in the presentations he had given across decades, in the technical papers he had written about mass production methodology and its strategic implications. It became part of German engineering education, a cautionary tale about the critical importance of aligning industrial philosophy with strategic requirements. The stopwatch that had timed the Jeep assembly was eventually donated to the German Museum of Technology in Berlin after Hoffmann's death, where it remains in a permanent display about industrial production during World War II. The descriptive placard explains its historical significance. This stopwatch, used by German automotive engineer Dr. Dieter Hoffmann to time American Jeep assembly in May 1945, it recorded 14 minutes and 37 seconds from major components to fully functional running vehicle, a revelation that fundamentally changed German understanding of industrial warfare and modern production. Methodology. Museum visitors often pause at that display, reading about the engineer who witnessed American production capacity and spent the remainder of his life helping others understand what he had learned. That modern warfare is determined in factories before it's decided on battlefields, and that industrial philosophy determines strategic possibilities more decisively than tactical excellence or weapon quality. The truth Hoffman discovered in Toledo, that America had already won the war through industrial capacity. Before Germany fully understood, the nature of the conflict became a lesson studied by subsequent generations of engineers, military strategists, and industrial planners. Never fight a war without understanding the industrial mathematics of victory. Never assume technical superiority can overcome categorical production inferiority. Never mistake quality for quantity when quantity differences are measured by factors of 10 or more. Hoffman understood that truth at tremendous personal cost. It shattered his professional confidence, undermined his technical identity, and burdened him with knowledge that caused years of psychological struggle. But he ensured that truth outlived him, preserved in testimony and teaching, so that future generations would understand the lesson without needing to learn it through catastrophic defeat. Industrial capacity determines modern warfare. Underestimating an opponent's production capability is strategic suicide. These principles, paid for with millions of lives and learned through total war, must never be forgotten. The stopwatch sits silent in its museum display case, a mechanical witness to the moment when one German engineer realized his nation had lost, not on battlefields but in factories. In the 15 minutes it took America to build vehicles, while Germany was still building assumptions about industrial superiority that had never been true. That realization came too late to change the war's outcome. But perhaps, through engineers like Hoffman who bore witness and told the truth despite psychological cost, it came early enough to ensure the lesson would be remembered by those who came after. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.